Hello and welcome to part 2 of our gravity versus conventional divine and Tartarian science. Just going over part 1 and why am I doing this. It was all about global warming. Apparently the Earth has warmed up 1.4 degrees. According to me it would have expanded and shortened the solar year by 30 seconds. Since this is not the case, I'm sort of going back into first principles. And I think it's got related to gravity, so we're investigating gravity when therefore we're going back to the first point, which is Galileo and his experiment of dropping those two identical masses in size, but not in mass, those two cannonballs from the Leaning Tower of Pisa. And they fell to Earth at the same time, although they were different weights. So we are going to use, as I said in part 1, two identical objects in size but in different weight, and we're going to use a steel ball bearing and a zircon ball bearing. So I'll just give you a quick look at those. Also in part 1 we mentioned Tartarian science was this concept: did Galileo have knowledge of some advanced technology? You know, as we talk about this Tartarian civilization, which is supposedly a very advanced civilization that either died out or was wiped out by a reset by either mankind or God. There's strong evidence that this civilization existed. Well, yes, I did come up with something. Galileo in 1632, he came up with the concept of relativity. He had a group of rowers row a boat at a certain speed, constant speed, and he dropped an object from the mast, and as expected it fell at the foot of the mast. He also then had the rowers double the speed, and keeping the speed constant, he dropped the ball again and it landed at the foot of the mast. So 1632, he's come up with the idea of relativity, not 1905 as Einstein. So I think we can cross out Einstein and his claim to fame with relativity. Also, I said I would mention having a closer look at my electronics and the extra clock. So I think I'll just show you a quick shot of that extra clock and the electronics. Okay, this is my timer I had to make up. It's based on a 1 megahertz crystal chip. The D flip-flop does all my interrupt crunching, goes through a buffer chip into this main chip here, which is the asynchronous divider, which is based on the 748154 chip. I couldn't get a deal online package, I had to get this surface mount adapter. And it does all the number crunching and counts my binary counter. And I need this switch here. This has 3 positions to look at the other 3 8-byte number. I have to throw one of these to get the other 3 bytes. This board here is my collecting board for the all the interrupts and the lights and the LEDs, that the pickups. It's just basically a power supply and collecting point. The main timer, the other independent timer, is this FPGA board based on the Altera di Nando board, and it does all the software, main software, and it's my master clock. The other small board here is just a bridge board going from USB to TDL and giving me power. Just virtually everything runs off 5 volts. It's only very low current. FPGA is all low current. So that's basically my setup. It'll get a bit more complicated. I had to mess up things a bit here to fit this board in, but otherwise I'll try and keep it a bit more tidy. Also, we're going to look at this concept of divine number. Was G equal to pi squared. So it's G dash or G double dash at G equal to 10. So I believe he was looking at G equals pi squared, which would come out at 9.87, as our current one is 9.8. But I think G equals 10 was a little bit, and the metre would have been a little bit too small. So I believe the ramp is coming up with this number at this early stages yet, but I've got to modify a few mods to the ramp. But I'm coming up with G equals pi squared, which will be a divine number. And Galileo was a Christian, so it makes sense to me as well. Okay, we're going to change the angle from 1.5 to 3 degrees. So we're making our ball bearing fall faster now. As we approach Galileo's 5 degrees, we haven't got there yet, but the shallow angles gives us more indicator of what the planets are doing. They can influence, through frictional forces, we can influence that ball bearing and give us time variations. And again, that's what I think Galileo used the ramp for. Also, I think I don't think he believed Kepler that the planets went elliptical in an orbit, and the ramp certainly shows that, because any sort of slight any bump in that ramp will indicate a change in velocity, which would change in acceleration, which would show you come up, and the Earth would feel that on the Earth. So you can see that clearly on the ramp. So my gut feeling is Galileo was in house arrest for his own protection, unlike the narrative where the Catholic Church locked him up for saying something. Don't think he did that. I think that's my gut feeling anyway, personal view. All right, anyway, enough for that, and we'll get on to into the experiment now. Right, before I switch over to the mechanical release, I'll just give you a close-up of this magnetic release. And there's a small brass screw which captures the ball bearing and released. Just to give you an idea of the sensitivity of this, I'll just give the table a tap. Alright, here's a close-up of the mechanical latch. Operation is basically ball bearing is placed under the latch. Latch is latched. The ball bearing is given a slight tap to make sure it's home against the end stop. This electromagnet operates through the timers. This small magnet on the top here is just to increase the flux density and gives a greater speed of operation to the magnetic pull, and also dampens the any oscillations that would actually vibrate and touch the top of the ball. So here's this operation now, releasing it. There we go. Okay, let's get into the main aim of this experiment, which was to investigate two identical objects but of different mass falling. And we'll use the ramp, just like Galileo did, to evaluate this. Now we'll be using a zircon ball bearing and a steel ball bearing using the mechanical latch, because I can't use the magnetic latch on the zircon ball bearing because it's not magnetic. Both ball bearings are 19 millimetres, which is the 0.75 of an inch, the old imperial size. Ball bearings are still made imperial in many cases. Zircon's 11 grams versus 28 grams. Also, we'll investigate this friction in relation to the Earth's journey around the Sun. The ramp is a perfect model to measure external forces, and as in Galileo's situation, And mine, I'm using the frictional forces to represent the planets. For example, if I was to use an optical interrupt on the Earth as it went around the Sun, it would take exactly the same time every year to an order of accuracy of 0.1 times 10 to the minus 13 in time and distance. So therefore it comes back the exact same spot to this magnitude of it. It's incredible precision, which can't be explained. So in other words, if the planets were situated here, Mercury, Venus, Mars and Jupiter, say, in this year, roughly here, it comes back to this same spot, which can't be explained if they're also in alignment, and the force would be more direct. So how come it comes next year with planets in a different situation, comes back, an optical interrupt will detect, came back to the exact same spot again? Can't be explained. So Einstein, why did Einstein, this thing of Einstein and relativity, it might be able to fit this in as well. Is Einstein associated with inventing relativity? It was clearly Galileo with his boat experiment. So why this lie? Also the elliptical orbit. I will show you the ramp with a ball bearing rolling down the ramp. It hits a slight bump. That's equivalent of an elliptical orbit where the Earth would have had a change in direction, and we on Earth would feel that if the Earth actually changed in direction. Unlike if we went around a perfect circle, we wouldn't be able to detect that. That's just a linear velocity. But a non-linear velocity, which was an elliptical orbit, as it would bounce or we'd feel that. Now, according to our Earth and many of the planets, according to Kepler's law, the elliptical orbit is greater than 0 but less than 1. But you'll often see the figure of something like this point, with say 8 zeros and a 1. Well, to me, a circle with that much deviation is still a circle. It's not an elliptical orbit. All right, so let's get into our experiment now. Right, here we go, demonstrating the effects of an elliptical orbit on the Earth. Here we have our counter inclined plane measuring 2.8. Let's give that a tap, see if I can get that to... Okay, we've just got that to 3.1 at the moment. 2.9. All right. Now the aluminium slide is a perfectly ground. I'm running my fingernail along there. I cannot feel any deviation. However, there is slight deviations in it that the ball bearing can pick up, and you might hear it as the ball bearing rolls down the ramp, and you might hear it hit those little tiny imperfections, which the incline measuring device will pick up, which is the equivalent of the Earth having a change in direction from an elliptical orbit, which we would feel. So here we go. I'll just send the ball bearing down. Now you might see that counter changing. That's detecting the small imperfections. Okay, so I'll do some runs now with the steel ball bearing and the mechanical latch. Try not to touch the ball, as my body heat may alter its size. Okay, I think that's enough watching the paint dry. We'll go now to our zircon ball, but I'll just do a few more runs so we get some on the computer. Okay, we'll do some runs now with the zircon ball bearing. We're on 3.1 degrees, that'll vary obviously. Giving that a gentle tap to make sure it's home. Okay, we dropped down to 2.7. In fact, I'll go to my calibrate point now. I'll activate the laser. And it still hadn't changed on the far wall, but it probably won't pick up 0.2 of a degree or 3 of a degree. The laser beam's about the size of a pencil head tip, so it'll take probably at least 20 metres to see a deviation, so I haven't got 20 metres to play with in length, but you will pick that. The laser goes to a self power save mode. Okay, what I'll do now, there's a lot of people probably be interested in the sound of this. I'll just put my lapel mic closer so you can actually hear the noise. That's picking up the small variations in the aluminium slide. Now they're probably, I can't feel them with my fingernail, as I said before. They're absolutely smooth as, but that ball bearing can pick it. Okay, that would be as I said before, I know I'm harping on it, but it would be an elliptical orbit. You would feel that on the Earth. Okay, look, I think I've had enough runs now for that and bored you to death with the paint drying. I'll collect this in data and show it to you later. Okay, I'll just do a sanity check to compare the speeds of these two ball bearings. I have the steel ball bearing trailing the zircon ball bearing. Just see if there's any separation. No, I couldn't see anything separating there. I'll do a longer run. No, it doesn't appear to be any separation. So that would indicate to me that they're either travelling at the same speed identically, or the steel ball bearing's faster. So I'll reverse that now with the zircon ball bearing trailing. Okay, I could see there that the steel ball bearing got ahead a bit. Yeah, okay, steel ball bearing got ahead a bit there. I'll just do a smaller run with less kinetic energy, see if I can pick up something. Yeah, okay, there's clearly that. Alright, so obviously now the friction test will be steel ball bearing and a known friction coefficient. I'll take it further up the ramp. Okay, clearly there's it's clear to me that that ball bearing has got more potential energy overriding the friction. The zircon ball bearing of less mass. Okay, look, my gut feeling would be on that would be that the Earth is coming up to meet the object rather than the object being attracted to the Earth. But I'll have to think of this a bit more. I'll have to consult my expert. But to me, that would indicate to me the Earth is coming up to meet the objects, as opposed to what we believe somehow that there's some gravitational force involved, some attraction or whatever. Two identical masses. I'm sorry, objects. I don't know. I have to think about that, but don't quote me. Okay, we'll just sum up the data now, and we'll use the first row of the steel ball bearing to evaluate this data. The first number you would have come across is this minus 0.018 number, which is 18 milliseconds. That's a minus number because we use that to evaluate our data. It's not a part of the calculation, and it's why it's a minus number. And it's the time the computer sends the signal to the coils, and actually the ball bearing breaks the first leading edge of the first optical sensor. And sometimes we use that to see if there's a stickiness on the back of the backstop of or there's something catching, like a bounce or anything that could. We like to keep that figure really small and constant, mainly constant. Yeah, always round about this, whatever it is. If it's trying to keep it around about 20 milliseconds perfectly and it doesn't vary. The next number was a 0, that's t equals 0, the start of everything. The next number you would have seen was a 0.094, which was the transit time through the first optical sensor. The next number was 2.5, which is the total runtime from the leading edge of the first optical sensor to the leading edge of the last optical sensor. This 0.003 was the transit time through the final optical sensor. So it starts off and it takes 94 milliseconds to go through the first one and 3 milliseconds to go through the next one, the last one. So imagine what it's going to be like when we go to 5 degrees. This number's really going to get small. Now the steel ball bearing was, it was the slower of the two, of 2.5 average, and from the highest to the lowest reading we've got 33 milliseconds, which isn't too bad. I'm aiming for around about 10. That shows me the ramps were very accurate. The zircon was a little bit was the faster of the two, and we were a bit surprised about that because we thought the ball bearing, the steel one, was with that pencil thing. We would have thought it would have been faster. So it had 56 milliseconds from its highest to its lowest. Next part 3, we'll be modifying the ramp. So I want to get more accuracy. I want to try and get to that pi squared for my little thing for gravity, the 9.87 number. We're back on this perpetual motion. I think we've been sort of conned here and told something that we shouldn't, someone's been lying to us. The solar year, according to me, should get shorter by 30 seconds. you know, if the Earth has increased in temperature by 1.4 degrees, it's definitely expanded. So I'm using this four S's now. This is my sort of little catchphrase now on the 4S band. So it's the time from the shortest shadow of the summer solstice of one year to the shortest shadow of the summer solstice of the next year. Blah, blah. I think I got that right. And it's always exact. Never changes, even though the Earth has expanded. Go figure. So climate change, is it really happening? Okay, thanks for watching this, and hopefully we get something for part 3 soon and a more accurate ramp. Thanks again.